0.7 goes right along with 0.6. There's the reason why we cover those together. And that's because logarithms are connected with exponentials. So our learning goal for the day is I can apply properties of logarithms and the graph of logarithmic functions. So to kind of introduce this, I want to go back and review really quick the graph of y equals 2 to the x. All right, we know that it's exponential, right? Base of 2, exponent in the power, or variable in the power, excuse me. So we know it crosses at 0, 1, and if I plug 1 in, I get 2. That's one of those properties we talked about. It comes in along, has a horizontal asymptote, comes along and curves up that direction. So one thing we talked about right at the beginning of our review, when we started reviewing beginning of this year, is we talked about the vertical and horizontal line test. Right? If I do a vertical line across there, it's definitely a function, right? Exponentials are functions. When I plug in an x, I only get one y back out. But something else it has is it passes the horizontal line test. Right there, even though it looks like it touches more than once, we know that it's getting closer to 0. And so there isn't a point where for 1y you get more than 1x, right? It passes that horizontal line test. So it's also a one-to-one function. But one thing we talked about is that if it's a one-to-one function, it has an inverse. So let's go ahead and graph it. Remember, we switched the x and the y axis. So instead of being 0, 1, it'd have a point at 1, 0. Instead of having a point at 1, 2, it'd have a point at 2, 1. Instead of having a horizontal asymptote on the negative x-axis, it's going to have a vertical asymptote on the negative y-axis. So it comes like this. It's going to be curving out that direction. So we know what the graph looks like. We have a graph of its inverse, but let's actually try to find the equation for its inverse. And this is where it gets a little tricky, right? Our steps were to switch the x and the y. So x equals 2 to the y power. And this is where we have a problem because the next step is to solve for y. Well, to solve for y, I have to get y out of the exponent. There is no way to do that. I can't take the y root because y is always changing. If it were squared, I could take the square root of both sides, but the y is a variable, it's always changing. So what happens is there's no direct way to switch that around or to get it in the y equals form. So there was just a notation invented, and this notation is called logarithms. And what they said is, well, since there's no way to solve for y, but obviously look at that graph over there, the black one, right? Obviously it has a graph. So what we're going to do instead is just rewrite it. And the way they rewrote it was like this. They said, okay, if you have a situation like this, you can write it as a function in the y equals form by going like this. Y equals log base 2, right? Because that's a base of my exponential up here, of x. So the way you write that out is y equals log base 2 of x. That's how you write that out. But those two mean the same thing. Like those are the same thing. So what that means is you can have an equation, you can write it in exponential form, which then it'll look like this, or you can take that same exponential form and write it in the logarithmic form, and then it looks like this. So you just have to know how to switch back and forth. So when it's in logarithmic form, the power, the y, comes over here, that's what it's equal to. The base is still 2, that's the base up here, that's the same. And x is like what the answer is, like what it comes to be out there. Okay, we'll practice switching back and forth on that. The book has a big paragraph here. We'll look at it right now. It kind of talks about these logarithms, right? They used y equals e to the x, which we'll talk about that, right? But it says if f of x equals e to the x is 1 to 1, it's continuous and increasing, so it has to be, then it has to have an inverse. But if you switch the x and the y, we end up with this. Hey, there is no way to take that and isolate the y. Like there's no algebraic steps or methods that we can do. So we have to have a way to define it, and the way we do that is by using logarithms. Now, this one's a little bit tricky. If you use what we just talked about, if I have x equals e to the y, I just said you would go y equals log base e of x. That's the way you would write that, using what we just talked about. Now, the tricky part here is when it's log base e, it's the one that occurs most often. It occurs a lot in natural growth. When you talk about whether it's like interest earned or population growth, this is one that comes up a lot. So E is called the natural base. So when I switch it, there's a shorthand for y equals log base e. So it's this, y equals the ln of x. So just know that y equals the ln of x and y equals log base e of x, they're the same thing. Okay, it is called the natural logarithmic function. So here's our inverse, right? The inverse of f of x equals the ln of x, which is really just log base e of x. Down here it has that other notation, right? If I have a to the x power, f of x equals a to the, its inverse of that would be the inverse of f equals log base a of x. You're just switching the x and the y. Okay, down to the bottom it says, right, note that log base e of x is usually written as the ln of x, right? That's the one we just talked about. So if it's a base e, ln of x is just a easy shorthand way of writing it, right? It's like French, it's like log natural, right? Natural log. Log base 10 of x also has a shorthand way of writing it. You can write that as just being log of x. So log base 10 of x is the same as log of x. So if you see an ln, just know it's log base e. If you see a log without a base, then it's base 10. And it's referred to sometimes as the common log. It doesn't say that here, and that's fine. Okay, so things we know about logarithmic functions. Let's go back and look at the graph for a second. So it's this black graph over here. Right, things we know. This function is always increasing. Okay, it's always increasing. The domain, right, it starts, if we run that horizontal line across, the graph doesn't start until it gets to 0, and then it goes to infinity. So it goes from 0 to infinity. Hey, by the way, up here on our exponential, do you remember that our domain and range was all real numbers, and the range was 0 to infinity, right? So now look at the domain of this one. It's 0 to infinity, and the range is all real numbers. So you can see how those two just got flip-flopped, right? The domain and the range, which is what happens when you find the inverse. The x and the y just switch places, or they're just flip-flopped. So that's what it's saying here. It's continuous, it's increasing. Hey, this one is concave down. Think of the upside down smiley face, right? Concave down, it is 1-to-1. Instead of having a horizontal asymptote, it has a vertical asymptote. So what it's saying as x gets closer to 0 over here, y goes to negative infinity. Really, this is the same thing as saying this. As x approaches 0, y approaches negative infinity. In other words, as x goes closer to 0, y is going down. But they write it with that limit notation. Again, we'll get into that more when we talk about limits. Hey, instead of having a point at 0, 1, a y-intercept, it has an x-intercept at 1, 0. And the next key point, instead of having the point at 1a, it has a point at a1. So right, the x and the y are just switching places. All right, so it says compare these characteristics. So if you look back, you should see that in all those cases, the x and the y's are just switched. The domain and the range is just switched on all of those. So a lot of times when I'm graphing a logarithmic function, I think of the exponential function first of its inverse, and it makes it easier to draw a sketch of. So it says use a calculator to graph y equals the ln of x, y equals log of x, so it's base 10 of x in the same coordinate plane. Do you see any similarities of the graphs? Go ahead and pause this and draw a sketch of what it looks like, and use your calculator or the computer or whatever to draw what these look like, and then we'll talk about that. So pause it and do that, then we'll come back together. So what you should have seen is with the ln of x, right, instead of having the point at 0, 1, it crosses at 1, 0. And normally with exponentials, it's at 1, 2.7. This would be at 2.71. We're just switching those x's and y's. And it has that vertical asymptote as I get closer to 0. So it looks something like that. When you go to graph the log base 10, okay, it still crosses at 1, 0, but now the next point's at 10, 1, which is right over there. So it comes along there, hits that. Okay, it's curving that direction. So it's just a little more extreme with the bigger the base gets, the more extreme it gets, like it's going out further faster. But if you look at those, there's definitely a connection between that and the exponential graphs that we've graphed in the last one. Okay, so now it wants us to graph this exponential or this logarithmic function using transformations or adjustments. So this is a little bit tricky. We've got two things happening here. Right? I've got a -2 on the inside. X minus 2 shifts it left or right. In this case, right. And then I've got the absolute value on the outside. What that does is take everything below the x-axis and reflect it up. Start with the inside one first. So we're going to shift it right 2. So if normally it crosses at 1, 0. Now it's going to cross at 3, 0. Normally next with the ln it has a point at 2.71. I'm going to shift it over 2, so it's going to be at 4.71, somewhere in there. And it's going to have this vertical asymptote at 2 because it's been shifted right 2. So it's going to come up along that, a couple on that, going to look something like that. Now that's without the absolute values. That's just shifting it right to. Okay, the next step is this, is that absolute value, remember, takes everything below the x-axis and reflects it up. So I'm going to do my final graph in red. So everything above stays the same. This part's going to stay the same. But to the left, take this graph below and reflect it up. It's going to be something like that. Kind of a cool graph. So that's that red one right there. So again, nothing new there. That's just taking, now we know how to graph logarithmic functions, and we're just doing the adjustments or transformations with it. Hey, we talked about this, right? We can change the form, right? If I have x equals e to the y, I can take it and switch it around so it becomes y equals log base e of x. So log base, right? That's log base e of x. So you can see where everything went. Down here I have x equals a to the y, so it becomes y equals log base a of x. So that's kind of what we talked about at the very beginning when we were describing what a logarithm is. So this wants us just to change the form. If it's in exponential form, write it in logarithmic form. If it's in logarithmic form, write it in exponential form. This first one's in exponential form, so I'm going to write it as being 4 equals log, and the base is 3, so the base stays the same. And make sure you write it as a subscript down below. Log base 3 of 81. Those mean the exact same thing. This means 3 to the 4th power equals 81. They're the same thing. Okay, let's write this one. This one, the power is always y. 0 equals log. My base stays the same. It's base e of what it equals. So again, those two are the same thing. What it's saying is e to the 0 power equals 1. That's what a logarithm means. Okay, this one's in logarithmic form. We're going to rewrite it. Just be careful. You have to have a base. This one doesn't have a base. That means it's base 10, right? That's what we talked about. So I'm going to say 10, and this is my power on the right side. 10 to the negative 1 equals what I'm taking the log of. So 10 to the negative 1 equals. So again, those two mean the same thing. Just two different forms of writing it. Let's see. This says, since e to the 0 equals 1, what does the ln of 1 equal? So just think about this for a second. This is log base e of 1. So remember, it's e to this power over here equals 1. Well, e to what power equals 1? It's e to the 0. So the ln of 1 is equal to 0. Over here it says e to the first equals e. Okay, so if I rewrite that, right, this is base e. E to what power equals e? That means e to the first power. So the ln of e is equal to 1. Hey, what that means down here, it says natural exponential functions and natural logarithmic functions are inverses. Right? Logarithms and exponentials, if they have the same base, they are inverses of each other. So if I have the ln, the log, ln means natural log base e of e to the n, they just undo each other. Same thing here, I have e to the power of the ln. They just undo each other. My answer is just n. So whenever you have the ln of e to a power, or you have e to the ln, they're going to cancel each other out. It's just going to equal whatever's on the inside. In this case, it's n. Okay, so we're going to use that idea just to simplify these. If I have the ln of e to the square root of 2, well, the ln of e just cancels out. Right, they're inverses. Okay, b, e to the ln. Again, e to a power of ln, they're inverses of each other. They just cancel out. My answer is just 3x. C, I have 10 to the, no, there is no base here, so that we'd say that's base 10. So I have 10 to the log base 10 of 2. Again, 10 to a power of a log base 10, they're inverses of each other. That would just be 2. D, log base 2 of 2 to the x squared. So again, log base 2 and 2 to a power are inverses of each other. They just cancel out. That comes out to be x squared. Okay, here's some properties of logarithms. It turns out there's many times in calculus that we want to take a logarithm and break it apart into smaller pieces. That makes it easier to work with. Or sometimes we want to combine it back together because it will be easier to work with. So we want to be able to know how to do both. So if you have a logarithm, if you're timesing on the inside, when you split them apart, you add. This has to do with those exponent rules. Remember we talked about if you times things at the same base, you add their exponents. It has to do with that. We're not going to get too deep into it, but just know that. Okay, if I'm dividing two things at the same base, I have the ln of a divided by b. Okay, well, if I times, I added. So if I divide, I subtract when I split them apart. If I have the ln of a to a power, I can take that power and drop it down in front. So those are your three main exponent rules. Just know this. This only works if both a and b are greater than 0. When you take the log of a number, it has to be greater than 0. And it has to do with exponentials. When you talk about an exponential, the base always has to be positive. Well, the logarithm is really an exponential in a different form, so the base has to be greater than 0. So these properties only apply if that's true. Okay, so A, the ln of 5/8, we want to expand it, we want to like break it into separate logarithms. Well, I'm dividing, so my property says the ln of 5 minus the ln of 8. Right? If I divide, I subtract when I split them apart. B is kind of complicated. One little trick that will help you is if you ever have the cubed root, write it as a power. Cubed root is the same as a 1/3 power. We'll do that a lot in problems to make them easier to work with. Well, now we can apply that third rule. I have a power up here. I can take it and drop it down in front. So I have the 1/3 ln, hit that dead spot on my board, 1/3 ln of x squared plus 1. Now you have to be careful here. If I want to break this inside apart, sometimes we try doing that, but the only way I can do that is if either they're times or they're divided. Well, x squared plus 1 they're not multiplied together or divided. So I can't really go any further past that to expand it out. 7 is doing the opposite. Now I've got these logarithms and I want to condense them. We can go backwards. If I'm adding two separate logarithms, we can combine them by timesing the inside of the logarithms, but I cannot do that as long as there's a number out in front. So if you do have a coefficient, a number out in front, you have to put it back up in the power before you combine them. So if I move the 3 up there, I would have the ln of x to the -3 plus, and I move the 5 up there, so I'd have the ln of y to the +5. Okay, now since they're added together, and now there's no coefficient out in front, now I can combine them. It'd be the ln of, because I'm adding, I'm going to times them, x to the -3 times y to the +5. Okay, that's really as far as I can go. I've combined that into a single logarithm. Okay, if you look at b, these are all ln's, but I do have this half, and I have that 3. Now this one doesn't have anything in front, so we're good there. So I'm going to move those up into the power. This would be the ln of x to the 1/2 plus the ln of x plus 1 minus the ln of y to the 3rd. Okay, so let's combine those together. I have 3 separate logarithms. The first 2 are added together. So when I combine those, I'm going to multiply them. X to the 1/2 times x plus 1 minus the ln of y cubed. Okay, now that they're subtracted, we're going to divide. So I'm going to end up with the ln of x to the 1/2, x plus 1, divided by y to the 3rd. It's going to go down below. So just look at that. When I was adding, right, they end up being times together. When I'm subtracting, they end up being divided. It ends up being on the bottom. Okay, I've simplified it as far as I can. So you know how to expand and contract logarithms. You'll be practicing with that. Okay, we want to solve exponential equations and logarithmic equations. We've already solved exponential equations, but this one's a little bit different, right? This one says solve for x. This equation is kind of messed up. When I say solve, I'm going to put a 0 there. So let's find out when it's equal to 0. If it ever does. Actually, it won't. Let's skip this problem. Okay, I'll think of another number there that we can plug in for y that will actually make it work, because 0 is not going to work. Well, let's do this other problem over here first. Let's do this logarithmic problem. So whenever you go to solve a logarithmic problem, my goal is I want a single logarithm equals a number. So I'm going to take these two, and I want to combine them together. So I'm going to go log base 2, and I'm subtracting. So it's going to be x over, I combine those two together by using subtraction. And the reason why I want to do that is because my next step is I can take that logarithm and I can rewrite it as an exponential equation. What I mean by that is I can rewrite this in exponential form. I'm going to go 2 to the 3rd power has to equal, I might come over here a little bit. So my board doesn't love working there. I go 2 to the 3rd power has to equal what's on the inside, x over x minus 8. So now I have an equation that I can solve. I have 8 equals x over x minus 8. You can times the x minus 8 over to this side to get rid of that. So now I'd have 8x minus 64 equals x. I'm going to minus the x over at the 8x and add the 64 over, so you end up with 7x equals 64. Divide by 7. And you just need to make sure that whatever, so I get 64 divided by 7, you need to make sure that whatever I get as an answer, it's not going to make a 0 on the inside. And what I mean by that is if I plug it back in here where I get the, remember we said you can only take the log of numbers that are greater than 0? Well, 64/7 is greater than 0, so we're good there. What about when I plug it in here? If I go 64/7 minus 8, I have to make sure that's greater than 0. Well, if you plug that in a calculator, 64 divided by 7 is like 9 point something. So 9 point something minus 8 is going to be a positive. So we're safe. That's our answer right there. So get it as a single logarithm. That's always your step number 1 right there. And then step number 2 is you rewrite it in exponential form. All right, let's go back to this example. I want to do an exponential equation. Let's go back to this example later. There should have been a number in for y. Let's say that we have, I don't know, 8. 8 equals, so y is equal to 8. So 8 is equal to, let me come down here. 8 is equal to e to the 2x minus 8 plus 6. And we want to solve that equation. So we have some different strategies for doing that. One is to get e, before we tried getting the base by itself, and then we try writing with the same base. So if I minus the 6 over, I get 2 equals e to the 2x minus 8. Now, if I want to write those with the same base, I have a problem. Like I cannot write base 2 as being e to a power, and I can't change base e either. So we've got to have a different strategy. So what I'm going to try to do is to cancel out the base e. And I can do that, remember what we just learned, if I take the ln of e, the ln of e to the 2x minus 8. The reason why I'm going to do that is because when I take the ln of e, they just cancel out. That's that inverse property we just talked about. So I have the ln of 2 equals 2x minus 8. Okay, now finish solving for x. I'm going to add the 8 over. Ln of 2 plus 8 equals 2x. Divide by 2. Divide by 2. That's my answer right there. And I can plug that in a calculator. Ln of 2 plus 8 divided by 2, and get a decimal, round it up to 3 decimal places. That's great. But again, the idea is this, is get the base by itself. And then if I can't make the base the same like we did on the last assignment, you want to cancel out the base by taking the log of both sides. In that case, because it was base e, I took a log base e or ln of both sides in order to solve that. Last thing here is just change the base formula. Right? On your calculator, we have a log base 10, that's the log key, and we have the log base e, that's the ln key. So we have both of those. But we don't have logs of other bases. So there's a way to switch. And this actually is not just for plugging things in your calculator. It's also helpful later on when we get in calculus, we're going to use this. So you need to know this change of base formula. And all it says is this, is if I have log base a of x, I can rewrite it as being log of x over log of a. And in that case, they both have base 10. Or I could write it as being the ln of x over the ln of a. That way they both have a base e. You can actually choose whatever base you want, but because in our calculators it does base 10 and base e, I don't know why you would switch it to anything else. So if I come down here, log base 7 of 112, right? We don't have a log base 7 in our calculator, but I can write it as being either log of 112 over log of 7, or I can write it as being the ln of 112 divided by the ln of 7. You could plug both those in your calculator and just double check. They both come out to be the exact same thing. This one's hard to screw up. It's just something you're going to memorize. And just what you have to know is whatever you're taking the log of goes on top, right? Log of 112 or ln of 112. Whatever the base is goes on the bottom, right? Log of 7 or the ln of 7 when you're looking at that. All right, so we have another equation to solve here. I have find the exact value of x if 3 to the x plus 2 equals 6. So let's go ahead and solve that. There's no way to make base 3 and base 6 the same. So what I'm going to do is take the log base 3 of both sides. So I have log base 3 of 3 to the x plus 2 equals log base 3 of 6. The reason why I did that is that inverse property we talked about. log base 3 of 3 to a power, those just cancel out. So now I have the x plus 2 is now out of the exponent. X plus 2 equals log base 3 of 6. Okay, now all I have to do is minus the 2 over, minus the 2 over. This is what x is equal to, but I need to use my change of base formula to plug that in the calculator. So I'm going to take this first part, log base 3 of 6. I'm going to write it as being the ln of 6 over the ln of 3. Oh man, sorry. I'll move over here. The ln of 6 divided by the ln of 3. Right, that part came, let me do a different color, that part came from right there. I just used my change of base formula to rewrite it, so now I can plug that in my calculator. If you want to write it as being log of 6 divided by log of 3, it doesn't matter. You'll get the exact same answer. So that change of base formula comes in handy in solving. It also comes in handy later in calculus when we go through and discover some stuff. That's what you're going to be practicing, and there's a lot of properties. You got to go through the properties of logarithms, and you got to go through the, what do the graphs look like, graph them using adjustments, and then you'll have some equations to solve also that you're going to work down through. Thanks, guys.